moment, which is shortly called magnetic moment, and the modern expression for both the classical definition and the modern definition. So the magnetic moment or magnetic dipole moment is a vector, first of all. Classically, we knew about bar magnets. So the bar magnet consists of north pole and south pole. The magnetic moment, which is a vector, directs from south pole to north pole. So the magnetic moment of this bar magnet, which is represented by the letter M, is given as strength of the poles, which they called pole strength. Pole strength multiplied by the length of the magnet. So the length of the magnet, for various convenient purposes, we take it to be 2L. 2L is just the length between north and south, because sometimes when we find the distance of some point, we will not find from north or south, we will find from here. Say for example, suppose a north magnet is here is a point. So this is north pole, this is south pole. What we do, we often write the distance from the center is x. Suppose if we consider the total length as L, distance from the north pole is x minus L by 2, distance from the south pole is x plus L by 2. To avoid this inconvenience, what we take is the total length as L, hence from the center this distance is L, this is L. Hence, instead of writing like this, distance of the north pole from the center, from here to here it is x, this length is L, this length is L, hence it is x minus L, and distance of the south pole from this point is x plus L. For this kind of convenience, we take the total length of the magnet as 2L. So the magnetic moment or magnetic dipole moment of a bar magnet is pole strength multiplied by 2L, which is called magnetic length. So the magnetic length will not be exactly equal to the length of the magnet. It is only about the 5/6 of the length of the magnet. Suppose you are having a bar magnet of length, let us say 12 centimeter, then the actual length is only 5/6 of the total length, 5/6 of the total length, which is 12 centimeter, which means that 10 centimeter, because at the poles the magnetic field would always be disturbed. Hence the effective length of the magnet is only 5/6 of the total length, or roughly about 0.8 times the geometric length. The total length is called geometric length and the magnetic length is little bit less than that. But here in our chapters or in almost all of the problems, we take the total length is almost equal to geometrical length. So magnetic moment is equal to pole strength into length, the magnetic length. So how we, in modern definition, we are going to prove that this magnetic moment is a product of current and area. So this magnetic moment's unit is ampere meter square, and pole strength, we do not know the unit, let us assume, and its length, the 2L is the length, its unit is meter. So the unit of pole strength is ampere meter square by meter, which is ampere meter. This is the unit of pole strength. How we defined the pole strength? The pole strength is defined as magnetic moment by length of the magnet. So which we can say magnetic moment per unit length, or per unit magnetic length. So this is how we define pole strength. Actually, this is a classical way of writing the magnetic moment, and this pole strength is very similar to electric charge. If you compare this with dipole, suppose two equal and opposite charges separated by a small distance 2d, then the electric dipole moment is from negative charge to positive charge, and hence the electric dipole moment P is given as Q into 2d, one of the charges into distance between them. Similarly, pole strength of the north pole, pole strength of the south pole are equal and opposite. So that pole strength acts as a magnetic charge into 2L. So we can write magnetic moment as magnetic charge into 2L. This magnetic charge is only called pole strength. So this is one interpretation. The other one, the magnetic moment of a bar magnet. Suppose you have a bar magnet and you have an electric dipole. You have an electric dipole minus q and plus q. At a distance r from the center, at a point on its axis, electric field is equal to 1 by 4 pi epsilon naught 2p divided by r cube, where p is the electric dipole moment. Similarly, from the center of a magnet at a distance d, the magnetic field is equal to 1 by 4 pi, it is not 1 by 4 pi, it is actually mu naught pi 4 pi into 2 times the magnetic moment by dq. So here P is written as Q into 2D and here M is written as small m, pole strength into 2L. So in the same way, if you have a current carrying loop, at a point on its axis at a distance x, the magnetic field is written as mu naught I. Suppose the radius of this circular loop is r, this distance is x, so we'll be writing mu naught I r square divided by 2 into r square plus x square whole power 3 by 2. This is what the expression of a magnetic field due to a current carrying circular loop. So let us try to just manipulate it a little bit algebraically. So it is mu naught I. So just here I am multiplying and dividing by 2 pi. When I do that, this mu naught will be there. This 2 into 2 pi becomes 4 pi into, this is 2 pi into r square is the area of the loop. So it is area of the loop and there is this current I divided by r square plus x square whole power 3 by 2. What if x is far greater than the radius? That means it's a tiny loop. It is at a far distance we are considering. Hence, in that case, when x is far greater, x square plus r square. Imagine two quantities like 100 square plus 1 square. It will be like 10,000 plus 1, which is almost equal to 10,000. So x square plus r square, which is almost is equal to x square. So here, next step, magnetic field becomes mu naught by 4 pi 2 into Ia divided by r square plus x square is x square whole power 3 by 2. X square whole power 3 by 2, 2 and 2 will be cancelled, x cube. Now compare the equation 1, 2 and 3. So in magnetic field, it is mu naught by 4 pi. In electricity, the constant is 1 by 4 pi epsilon naught. Here 2 at a point on its axis. This is magnetic moment. This is electric dipole moment. Then this must be, Ia must be equal to magnetic moment. Using this expression, we know that a current carrying circular loop at a far point, current carrying circular loop or coil, behaves like a bar magnet at a very far distance. Bar magnet at a far point or at a very far distance. So comparing all this, we have got a new equivalent of magnetic moment, which is current into area. Classically, magnetic moment is defined as pole strength into magnetic length. In modern definition, we define magnetic moment as current into area. Suppose you have a n number of turns. There are n number of turns. Then the total magnetic moment of a current carrying loop will be equal to n times current into area. This alone gives the unit for magnetic moment, which is n number of turns, no units, and current is ampere, and area is meter square. So ampere meter square. So there are three quantities. Now we have seen magnetic moment is current into area, which is also equal to pole strength into 2L. So the unit of magnetic moment is ampere meter square. The unit of pole strength is ampere meter, because when it is ampere meter, and this length is meter, hence we get ampere meter square as the unit of magnetic moment.